Welcome back, everyone. Today we start Chapter 6, and I'm here on the first page of the Chapter 6 lecture note outline. In Chapter 6, we're going to be learning about chemical reactions and the equations that we use to describe those reactions. And that's actually where we are going to start today's lesson. We're going to start here in the first part of learning about chemical equations. Chemical equations explain the transformation of substances. And in this section, you'll learn to read and write simple chemical equations for reactions. So let's get started here in part 1. So first, let's look at the different parts of chemical equations. So I have an example written here. The first thing we'll talk about is what is on the left-hand side. And we call the left-hand side of things written on a chemical equation the reactants. That's where we put our things that are reacting with each other and the environment that they're in. So we put these on the left. So I'm going to write down here in this table, reactants are found on the left-hand side of an equation. And you can think of reactants as being a lot like the ingredients in a recipe. So this is also called our starting materials. So I'll write down also known as starting materials. And again, these are similar to the ingredients in a recipe. Now, on the other side of a chemical equation, this is the results side, we have what are called the products. And products, there might be more than one or there might be one. These appear on the right-hand side of an equation. And again, these are the results of the chemical reaction that's taken place. So really what this is showing in a chemical equation is what species on the left, the reactants, what those do and how they change into products. So it's a change from the left to the right, kind of like when you read a sentence. Now you will also see the prevalence, the appearance of plus symbols, what they look like addition signs. And those are designated to appear, they mean something on the left and on the right. What they really mean when they appear on the reactant side is that we have to put these different reactants together. So they have to be in contact with one another. That might be in the same reaction flask, or if it's a gas, they might be in the same container as each other. Either way, they have to come in contact with one another. On the product side, that plus symbol means that the products are formed together, so they're both produced in the same place as one another. Now, another thing that you will see included in a chemical equation are phase symbols. So some of the symbols we use include S for solids, L for liquid, G for gases, and then we also see a lot the symbol AQ, which means aqueous. Now, if you don't know what that means, what aqueous means, it means that thing, whatever that thing is, has been dissolved in water to make what we call a solution in water, or an aqueous solution. So for example, you might have, say, solid sodium chloride, right? Solid sodium chloride, we would write that NaCl with a little solid next to it. Now, when we put that into water, it doesn't melt. It does what we call dissolving. Now, if we had NaCl, that means we liquefied it. To make NaCl as a liquid, we would have to heat the solid stuff up to something like 800 degrees Celsius for it to melt. That's not the same as if we dissolved it in water. Now, if we take solid sodium chloride and put it into water and stir it around, we can do that at room temperature. We would represent that with the symbol NaCl with an AQ next to it to represent an aqueous solution. All right, let's scroll back up to our example chemical reaction and review some of this terminology. So here on the left-hand side, I have the starting materials, or reactants. Notice that in this case, I have two reactants, and necessarily they are separated by a plus sign because there's more than one of them. So we have the reactants on the left-hand side, and then on the right-hand side, we have the products. In this particular example, there's only one type of product, this NH3 formula. If there were more than one type of product, we would have a plus sign, and then the formula for those different products would be written also in this area. We also have the phase signs, or the phase symbols, indicated next to each of the formulas. So in this case, nitrogen is a gas, and it's required to be in the gas state for this particular example. We also have hydrogen gas located here, and then the product in this case is ammonia, but notice the phase of ammonia is indicated as an L. That's telling us that ammonia in this example is being formed as a liquid. All right, now that we've learned about the fundamental parts of chemical equations, we're going to go on to the next page and learn a few more details. Specifically, we're going to look at the meaning and different styles of arrows that we can have in chemical reactions, and we'll also learn about ways that we use information both above and below the arrow to indicate some more information about how a reaction is occurring. Okay, so another really important part of a chemical equation is the arrow that we see. And what does that arrow mean? Well, what the arrow does is it kind of serves two purposes. Number one, it separates. It's a marker that says, hey, there's this stuff over here at the beginning and there's stuff over here at the end. So it separates the reactant side from the product side. And that's an important thing. And really what it's doing there then, if it's separating reactants from products and reactants are turning into products, what the arrow really is representing is how change is occurring and the direction of that change. And usually we write them down showing the direction going from left to right. Okay, so far so good. And now we get to something that I think is not nearly as well understood for chemical reactions. And that would be called the coefficients. Coefficients are numerical values that appear beside each of the reactants and or products that we have in a chemical equation. What these mean, these numerical values mean, is how many units of that particular species, that particular molecule or salt, that formula units wise, it's like a multiplier on the formula units that tells us how many are either used if it's a reactant or how many are produced if it is a product for each time the chemical reaction runs, one cycle of it. So it's a multiplier that tells us the mass that's produced. And what these coefficients are used for is something called mass balancing, which is what we're going to look at in a little bit. Before we do that, though, let's take a look at the different types of reaction arrows. So I mentioned reaction arrows up above, and I like to, before we get into balancing, just go and show you something you might not have known before. So a lot of times when we see the arrows, we see them drawn like from A to B going forward. That, of course, means a forward-favored reaction, a reaction that goes from left to right. Now, it turns out not all reactions actually do that, even though we usually write them that way. They don't always favor B. What can happen when you do an actual experiment is you discover that a reaction runs kind of backwards to the way you think it would run. And that we represent as an arrow, which we drew here, which would be B going to A. Now, normally I would rewrite that with B on the left and then A on the right so we can have a forward arrow, but this is something to just take note of. We also more frequently see a reverse arrow. So we see an arrow going forward and an arrow going backward. And this is what we call a reversible reaction. And there are some variations on these arrows that you'll often see, and later on especially I will show these to you. We see sometimes an arrow where the top forward one, which I've drawn here in the top, is larger than the bottom one. We call that a product-favored reaction because most of the reaction is making B and only a little bit is making A. There are also cases where we have B and A where it's a reactant-favored reaction, and that would be like the one I've shown there. Another point is that we often use symbols both above and below the arrows. So for instance, we might have a little triangle under an arrow where there's a reaction going from A to B. That little triangle, what that means is the ancient symbol for heating. It actually goes to even pre-alchemical times. It kind of symbolizes a little fire, like a little pyramid. That's actually where it comes from, a little triangle. And it means heating. Now, we don't often use fire to heat things in the lab anymore. We usually use a hot plate because it's safer. We also see a lot of times catalysts that are used in a reaction. A catalyst, you'll learn, is something that isn't a reactant or a product because it doesn't get consumed or produced. It just is utilized to cause the change to occur. So it exists in the same amount at the beginning and at the end, but facilitates the change going on. This is called a catalyst, and because it's not formally a reactant or a product, we write it not on the left or on the right, but above the arrows. So usually how we're doing things to keep things as organized as we can, and this again is flexible, but usually the I guess I would say the convention is to write catalysts above the arrow and conditions below the arrow, whereas those are separated from the reactants and the products over here. So we separate them like this, and that's normal. Now, if you do it a slightly different way, probably no one is going to be that upset about it if you write the catalyst on the bottom, or if you run out of space on the top or something. So anyhow, that's those are the basic parts of a chemical reaction. And we've got coefficients, we've got arrows, we've got reactants, products, conditions, catalysts, all that kind of stuff. Now, what we're going to look at next is balancing chemical reactions and what that means and how we use and come up with those coefficients that are actually written. We're actually going to be writing chemical reactions, and part of doing that, the responsibility is to have the coefficients there. So you're going to actually learn how those are made and where they come from and how to get them right every time. So let's go to the next page and get started on that. Okay, so we're going to learn about balancing chemical equations here in part 2 of the chapter 6 notes. So what we're talking about here is something about the law of conservation of mass. To help you visualize the conservation of mass and what we're doing when we balance chemical equations, let's start first with a diagram, and then we can adapt this to an example chemical equation. So here in the diagram, I have the empty reaction flask where we're going to put the reactants. And the reactants I have in this example are reactant A and reactant B. And specifically, I have 50 grams of reactant A and 50 grams of reactant B. So I'm starting with a total of 100 grams of reactant that I'm putting inside of this reaction flask. Now, after some period of time together in this reaction flask, a chemical reaction takes place where A and B form a new substance together. You're going to be learning about the types of chemical reactions that can take place so that you can predict what might actually happen when you put some type of A or some type of B together. For now, though, let's assume A and B react in a very simple way where they form this compound, where A is attached to B. Now, after some period of time, the reaction actually stops changing. That's what we would say is the end of the chemical reaction. At this point, how much mass do we have inside of the flask? Has it changed? Has it increased or decreased? No. That's what the law of conservation of mass says, is that the masses that we start with will have to add up to the masses that we end with. Now, where do the coefficients come in, and what does it mean to balance a chemical reaction? Notice in this example, I have a certain number of A's and a certain number of B's. Let's count up the number of A's that we have. We have 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 A's there. Let's count out the number of B's. There's 1, 2, 3, 4. So we have 8 A's and 4 B's, and those went into our reaction flask. After the reaction takes place, notice that the product we're forming has a single A attached to a single B. So at the start of the reaction, before we combined A and B, they were individuals, and then we put them together into this flask, and a reaction takes place where the A's attach to B's, and we see the formation of products as such. Notice also that after the reaction is complete, we have a mixture. We have a mixture of products with some of the substance A that did not react. These are leftover reactants, just like the broccoli we don't want to finish at dinner. Now, if we were scientists studying this reaction, we would ideally want to describe this process with a chemical equation. We would analyze the reaction and look at the way in which A reacts with B. Specifically, we would look for the ratio at which A combines with B, and that would necessarily involve isolating as a pure compound the product. Once that product is isolated, it's possible to write down the net chemical reaction for this process. We have one of the A substance reacting with one of the B substance to form one product, which has the formula A attached to B. This is a balanced chemical reaction because all of the A and B on the left-hand side are accounted for in the product, which has one A and one B in the formula. So one of the things that I would like you to get from this diagram is the fundamental difference between the masses of things, that is what they weigh, and the coefficients that we write down in the chemical reaction. The coefficients tell us how many, whereas the mass tells us how much. It's a very subtle but important distinction. So as we learn about balancing chemical reactions, we want to keep in mind first that chemical equations must always satisfy the law of conservation of mass. Specifically, matter is not created or destroyed, only reorganized. So for us, what that means is that the number of reactant atoms that we have, so the number of atoms on the left, has to add up to the same number and same type of atoms on the right. Let me show you an example of what I mean by this. Suppose we had some chemical reaction that was taking place between a hypothetical substance X and a hypothetical substance Y. Let's say the compound that X and Y form when they react has the formula X with a subscript 2 next to it and Y. This would be like Y has two X's attached to it. So the formula of this product is necessarily X with a subscript 2 and a single Y atom. Now, if we look back at the left-hand side of this reaction, you might notice a problem. As it's written, it is unbalanced. How is it unbalanced? Well, take a look at the X on both sides and the Y on both sides. And remember, the number of reactant atoms needs to equal the number of product atoms. So if we look at this formula of the product, there are 2 atoms of X in the product. Y requires 2 X's attached to it. But if we look over at the reactant side, there's only 1 X written. How do we fix this situation? Well, your first inclination might be to put a subscript 2 next to the X, so that there's the same number of X's on the left as on the right. Now, can you see any problem by doing it in this way, by changing the subscript of one of our reactants? That's right, if we change the subscript of a reactant or a product, we're changing its identity. If we change its identity, we're all of a sudden talking about a completely different chemical reaction with different substances. We don't want to do that. We want to keep the reaction the same. We don't want to change the identity of any of the reactants or any of the products. So then you might ask the question, well, how do I balance the chemical reaction if I can't change the numbers down here? Well, that's where we have coefficients. Coefficients are the numbers that we can write in front of different reactants or different products that change how many there are, but not their identity. So I can balance this example by simply putting a 2 right in front of the X. Now all of a sudden I have 2 copies of X to go with my 1 copy of Y to form the new substance X with a subscript 2 and a Y. This is an example of how we balance chemical reactions. We have to make sure that the number of reactant atoms on the left is equal to the number of product atoms on the right, and we do this by changing the coefficients, not the subscripts. Now, in the next section of this lesson, I'm going to teach you how to actually balance chemical reactions. And we're going to start here with this first example. I'm going to walk you through the process, show you some tips, and then we're going to practice on a number of examples. So let's go ahead and get started learning how to balance chemical reactions. Now, as we begin learning about how to balance chemical reactions, I want to point out one thing. Here in the beginning, I'm going to show you detailed step-by-step how to go about doing it. Now, this might look like it's very time-consuming and lengthy, and yes, when you're first learning how to do it, it definitely consumes more time. But later on, and that is not that much later on, you're probably going to get a little bit faster at it, And you won't have to go through all of these individual steps. You'll be able to go through them much quicker. But here in the beginning, I want to make sure we go through those steps one at a time carefully so that you see how it's done. So let's take a look at this first example. On the left-hand side, I have a molecule called hydrogen peroxide. It has 2 hydrogen atoms and 2 oxygen atoms in the formula. On the product side, I have water and oxygen gas. Water has the formula H2O, so there are 2 hydrogens and 1 oxygen atom. And then oxygen gas is a diatomic molecule. It just has 2 oxygen atoms. The first thing that we want to recognize is that there's an implied number 1, the coefficient number 1, in front of each of these molecules on the equation. So that tells us we have at least 1 copy of each of these species. The next step in balancing is to look at the left-hand side and look at the right-hand side and make a comparison. What we're trying to do is find any atoms that there are not equal numbers of. So they're different on the left than on the right. So let's do a quick inventory. We see on the left-hand side that we have 2 hydrogen atoms in total. There's no other hydrogen atoms written over here. Let's look over at the product side and see if that matches. So we look over here and we see there are also 2 hydrogen atoms. That's good. That means hydrogen is already balanced. Now let's take a look at oxygen. Notice we have 2 oxygen atoms in the formula on the left, and on the right we see 2 over here, but there's also another one over here. That means we have a total of 3 oxygen atoms on the product side. That's an unbalanced situation and we need to fix it. We need to make sure that there's the same number on both sides. Now, one of the things to note is just because we have 3 over here doesn't mean that we have to have 3 over here. We can actually change the total number on this side to something like 6 or 12 or whatever we want it to be. As long as it matches on the left and on the right, that's what we're going for. So we need to change the coefficients in such a way to make all of the oxygen atoms and all of the hydrogen atoms add up in the end. Now, before we do this example, I want to scroll down a little bit and show you that there are some tips on how to achieve efficient balancing in the easiest way possible. There are a number of these tips that I'm going to introduce to you over the course of this lesson. And since you don't know them yet, each time I show you one, it's going to be something new. I don't want it to surprise you, and I just want to mention they're all documented here. And whenever we use one, I'm going to point it out, especially here in the beginning. So let's go look up here real quick. Before we do that, though, actually, let me point out this one, the first one. This is one of the most important ones that we use almost all the time. And actually, I have written these out in the order in which I think they're the most important, though they're all important. Anyway, we see it says, make odd-numbered atoms an even. So we're going to change, the idea here is we're going to change anytime we see an odd number of atoms on one side, we're going to try to manipulate the coefficients to transform it from an odd number into an even number. And that's actually the tip that we're going to use in this example. To see why this tip makes sense over here, recall what I mentioned earlier. We have 3 oxygen atoms on this side. That's an odd number of oxygen atoms. So what we can do to balance this is make that odd number an even number. And how we do that is we change the coefficient in front of the water molecule from an odd number to an even one. If we do that, it's going to make the balancing a lot easier. Let me show you what I mean. Let's rewrite this equation with a new coefficient in front of the water molecule. So let's write down H2O2, and then the arrow, and then let's put a 2 in front of water. Let's finish out the rest of the equation by writing in our 1 oxygen. So notice here on the right-hand side, I now have an even number of oxygen atoms. Now, if I look back on the left-hand side, we still have an unbalanced situation here, right? Because we have 2 oxygens on the left and 4 on the right. So it doesn't add up, it doesn't match. How can we fix that? Well, that's right. If we put a 2 coefficient now in front of this hydrogen peroxide, this H2O2, that means we would have 4 oxygen atoms on the left, and that matches with our 4 oxygen atoms on the right. It's now balanced. this step that I showed here where we rewrote the equation to rebalance one of the reactants or products, it could be, is called a rebalancing step. So I changed a coefficient on the right and therefore had to fix something else on the left, and therefore I rewrote it. We call that rebalancing the equation. So if we look at the two steps here in balancing this particular reaction, the first thing we did was we made the odd numbered atom, oxygen, even, and then in the second step, we rebalanced oxygen on the left-hand side. Now, what we're going to do is look at some other examples of balancing, and I want to introduce to you some of the tips that are in this box as we go through these examples. Let's take a look at this reaction. On the left-hand side, we have two reactants. This first reactant, which has the formula H2SO4, is called sulfuric acid. And then we have this, which is called sodium hydroxide. We have the sodium cation with the hydroxide anion. That's a polyatomic anion, as you are learning those now. Our products are two. We have sodium sulfate and we have water. Now, this looks like a lot of atoms that we have to worry about balancing, but I'm going to show you some tricks to make this really simple. And I think in this example, there are at least 3 of these tips that I can teach to you. So let's start with one of them. One of them is a suggestion that, if possible, try balancing metals first. So what we can do is look at the reaction and try to find any metals on the reactant or product side and notice if they are balanced or unbalanced. If they're unbalanced, that's a good place to start balancing. So let's see if we can find any metals in this equation. Do you notice any? Pause the video and take a look. That's right. The metal that we have in this reaction is sodium. Notice that we have sodium over here and sodium over here. Also notice that the sodium, the metal, is unbalanced. What we're going to do is try balancing the metal first. So how can we balance the sodium on the left with the sodium on the right? Well, we have an even number of sodium atoms. We have 2 over here, and it would make sense if we had 2 over here. How can we do that? We can do that by putting a coefficient 2 in front of sodium hydroxide. So let's start by rewriting this equation with a 2 coefficient in front of sodium hydroxide. Now our metals are balanced. We have 2 on the left and 2 on the right. Notice that I didn't balance the sodium on the left by using a subscript. I only changed the coefficients at this stage in balancing. Now that we have the sodium, the metal balanced, what do we do next? Well, a good tip for this stage is to look at what else was affected when we balanced the metal. So notice that when I put a 2 coefficient here to balance sodium, I also affected something else. I affected the number of the atoms over here. Now we recognize this as the polyatomic ion called hydroxide. So before I had the 2 here, there was just a 1, I had 1 hydroxide, but now there's a 2 coefficient there. So there are 2 copies of this hydroxide. Now here's where a new tip comes in, and you're going to have to bear with me on this tip because it's probably pretty confusing at this stage, but I want you to be able to use it, so I want to show it to you now. Here's the tip. The number of hydroxides on one side of the equation will very frequently, if not almost always, be equal when it's balanced to the number of water molecules on the other side. That's because it turns out that hydroxide ions very frequently actually become water molecules in the course of the chemical reaction. So let's look at this. If we have 2 hydroxide ions over here, because the 2 is in front of this, that means on this side, we should have the same number of water molecules. So we can balance the hydroxide on the left with water on the right by putting a number 2 in front of water. Now, if you're like me, you don't like just believing in something because someone tells you it's true. So let me show you for a second why this works. When I see here the 2 in front of sodium hydroxide, what that means is we have two copies of hydroxide. Let's draw those. There's one of the hydroxides. It has the formula OH, and those are stuck together as a group, and that whole thing called hydroxide has a negative charge. But there's not just one of those, there are two. I know there are two because there's a 2 coefficient right in front of the substance sodium hydroxide. So let's draw the second one. And there we go. There are 2 hydroxides. So let's see why these hydroxides can be balanced with water. Let's look at what a water molecule looks like if we try to visualize it. We have a single oxygen atom connected to 2 hydrogen atoms. Let me show you what that looks like. That's how we can visualize a water molecule. Water is H2O, and really, if you think about it, it's simply a hydroxide connected to a hydrogen atom. So when we started balancing this reaction, notice that we only had a coefficient 1 in front of water. That's one of these. But notice that when we balanced the metal by putting a 2 coefficient in front of sodium hydroxide, that made 2 copies of hydroxide. Now, if we have 2 hydroxides, that means we have to have 2 waters, which is why we put the coefficient 2 in front of water. That's because each of these hydroxides is turning into one of those waters. And if we have 2 hydroxides, that means, of course, we have 2 waters. Now, you might ask the question, how on earth are those hydroxides becoming water? They need that hydrogen atom. Where is that coming from? Well, notice here on the left-hand side of the equation, there's a molecule, it's called sulfuric acid, that has those very 2 hydrogen atoms. Let me show you what this looks like visually. We can dissect this sulfuric acid compound into 2 hydrogen ions with a plus charge each. Remember, hydrogen is in group 1 of the periodic table, and a sulfate anion. Sulfate is SO4 with a 2 negative charge. So the 2 hydrogen ions that attach themselves to the hydroxide ions is where the water comes from. So we can balance hydroxides on the left with water on the right, and this usually works out very well. Of course, there are some examples where it's not like this, and I'll show you what those look like. But for now, that's a really good tip. Now let me ask you the question. Is this reaction balanced? To answer that question, we have to look at the left and the right-hand side and add up everything and make sure everything is there. Let's start on the left. And I think since we're doing this for the first time, it's probably a good idea to keep a little running tally as we go. And I'm going to start over here on the left-hand side and tally up the different things that we have on the left, and we'll compare that to the tally we get with the things on the right. So first, let's start with hydrogen, since hydrogen is the first element that we run into on the left-hand side. We have 2 hydrogens in this formula. That's, of course, because we have an implied number 1 here. I'll just draw that 1 in so we can see it. So if we have a 1 here, that means we have 2 hydrogens from this sulfuric acid. Okay, so let's continue and see if we find any other hydrogens. So we go over here and we say, okay, well, that's not a hydrogen. That's not, oh, there's a hydrogen atom. So, okay, we need to add that to our count. We have a number 2 here, and since the 2 is in front of this whole thing, we can say there are 2 hydrogen atoms. So that gives our total amount of hydrogen on the left-hand side the number 4. So we have a total of 4 hydrogen atoms on the left. Let's compare that with the right-hand side. Let's add up all of the hydrogen atoms on the right. Go ahead and pause the video and see if you can add up all of the hydrogen atoms over there. Notice that we don't have any hydrogen atoms in the first substance, so no hydrogens there. And then we get over to water and we see there's a 2 in front of water, and water has 2 hydrogens in it. So that means we also have 4 hydrogen atoms on this side. So it looks like hydrogen is balanced on the left and on the right. Okay, now let's go back and start with the next atom. So if we get over to the left-hand side, we run into sulfur. Now here's where I want to show you another tip with balancing. Whenever we run into a polyatomic ion like sulfate, it's very helpful to balance the entire polyatomic ion on both sides rather than the individual atoms. So for example, this note says, when we balance sulfate, it's helpful to think of it, say, as say, 2 sulfates rather than 2 sulfurs and 8 oxygen atoms, it gets very unwieldy to break this up. Since it's a group and it doesn't change from one side to the other, it's helpful just to balance it as a single unit. So let's see, how many sulfates do we have over here on the left? That's right, we have 1. So if we have 1 sulfate over here, let's go and see how many of those are on the right-hand side. Where is sulfate over here? That's right, it's only located over here. And how many do we have? That's correct, since there is a 1 coefficient right here, we have 1 sulfate on the right. So it looks like sulfate is balanced on both sides. Now we can finish up with the rest of the elements remaining to be balanced. Let's check out sodium next. So we see the 2 coefficient in front of sodium hydroxide, so we have 2 sodium atoms on the left, and then we go over to the right and we compare. Notice we have the subscript 2 in the formula saying that each of these formula units has 2 sodium atoms within it, and there's a 1 coefficient here, so we know there is a total of 2 sodium atoms on the right-hand side. So sodium is balanced on the left and on the right. The only thing we have left to balance are oxygen atoms that are not a part of sulfate, of course, because we balanced sulfate separately. Notice that we have 2 oxygen atoms over here on the left because of this 2 coefficient. Let's compare that on the right-hand side. Remember how we balanced the hydroxide with the water? That should make the oxygens balance. Let's just see how many oxygens we have on the right. The 2 coefficient there means we have 2 oxygen atoms on that side. So if we have 2 on the left and 2 on the right, that means oxygen is balanced as well. So that's an introduction to how balancing chemical equations works. On the next page of this lesson, you'll find that we have a number of other examples that I want to go through with you. And those examples might take a little while, so this could be a good point for you to pause the video and maybe take a break before you go into those examples. What you're going to learn in those examples are how we can use some of these same tips that we just learned about and a few new ones as well. So when you're ready to get started, go ahead and turn the page and I'll show you how to balance some other chemical equations. Okay, so let's look at this next example. We have something called zinc sulfide over here on the left, combining with oxygen. So these are our reactants on the left. Our products have zinc oxide and sulfur dioxide on the right. Now, the first thing you want to look for, really good place, is if you see metals, try to see if the metals are balanced or unbalanced. So what do you think about this one? Are the metals balanced or are they unbalanced? Well, notice that we have 1 zinc over here on the left and also 1 zinc over here on the right. So what does that say about the zinc? Is that a good place to start? Well, it turns out no, we're not going to be able to start with the metals here because the metals are already balanced. So we can't start with the metals. Now, that leaves you with the question of, well, where should I start? Where's a good place to start? And what I would say, another really good place to look for first is to find if you have any odd numbered atoms. So if you take a look at oxygen here, notice that we have 2 oxygens on the left, but we have 3 oxygen atoms total on the right. So oxygen is fundamentally unbalanced. And another really important observation, of course, oxygen would be a good place to start, but where do you start with it? Well, it turns out that if you see an odd numbered atom, so you have an odd number of oxygens, for example, there are only 3, that's a great place to start because it's going to be a lot easier for you to have even numbers on both sides. So what we're going to do is we're going to change the coefficient on odd numbered atoms to make them even. I call this make odd even, and it's a really common strategy to use. So what are we going to do? We're going to rewrite this equation, making the oxygen even on both sides. Now we can do that by putting a 2 coefficient in front of the zinc oxide, and that gives us 4 total oxygen atoms on the product side or on the right. And now, of course, we still need to balance the oxygen, but notice that we also need to rebalance the zinc. Because we've modified the oxygen on zinc oxide to make it even, we've also affected the zinc. So let's rebalance the metals by putting a 2 coefficient in front of the zinc sulfide. And that makes the zinc balanced on the left and on the right. So now we've fixed two problems. We have even numbers on the right, and we have the metals being balanced. Now notice when we rebalance zinc that what it does is it affects sulfur. And this brings me to another sort of general tip. When you have something that you're rebalancing, like the zinc here, when you put a coefficient in front of something, it often affects something else that is in the same compound. Now, that's the chain of events that you will follow. So if you affect one thing, if you change one thing and it affects another thing at the same time, that's what you should rebalance next. So it sort of tells you where to go step by step. So with this one, for example, we fixed oxygen, but that affected zinc. So then we fixed zinc, and now it's affecting sulfur. So now what we're going to do is fix sulfur, and then we'll be told what the final element to fix is. So let's take a look at how that works. Okay, so now we are rewriting the equation where we have the 2 coefficient in front of the zinc sulfide. That was, again, to fix the zinc. And then we need to fix the sulfur because that was changed by this fix. So we're writing everything else the same, but then we're going to also balance sulfur in the last term. So we need to put a 2 in front of the sulfur dioxide. That's in order to make 2 sulfurs on the product side to match the 2 on the left. Notice that it affects, when we fix that sulfur, it affects oxygen. So the last element for us to balance here is oxygen, and for that reason we should total up how many oxygen atoms are on the product side so we can fix that on the reactant side. So just to show you how we are arriving at these numbers in detail, we've got the 2 coefficient in front of the zinc oxide, so there are 2 oxygen atoms from that. And then we have the 2 coefficient in front of sulfur dioxide. There are 2 oxygen atoms in the formula of sulfur dioxide. So 2 times 2 is 4. So there are 4 oxygen atoms from this and 2 from this. So that gives us a total of 6 on the product side. Now we need to have 6 on the reactant side also to match. And that's where this 3 coefficient comes from, right? There is in the formula for oxygen, right? Oxygen gas is diatomic in its element state. So it's O sub 2. And to get 6 oxygen atoms from that formula, that means we need a 3 coefficient in the front of it. So that gives us a total of 6 on the left and 6 on the right. So oxygen, therefore, is balanced. And so are all of the other elements. Notice we have 2 zinc, right? We have 2 sulfur, and we have 2 sulfur. We have 6 oxygen, and we have 6 oxygen. And those are all the elements that are present. So in effect, this equation is balanced. So let's take a look at the next example and see how this one might be a little bit different. Now, this is a nice example here. What I would like you to do is pause the video and spend a little time looking at it and see if you can apply any of the tips that I've shown you so far to attempt to solve this one. So look at it and see if you can find, if you look back at the list of tips, a good place to start. And then when you unpause the video, I'll show you a good way to go about doing this one. So notice that if we look at the formula for P2O5, that's diphosphorus pentoxide, we have an odd number of oxygen atoms. And if we apply the odd make odd even tip, where we take an odd numbered atom and we change the coefficient in front of it to transform it into an even number, this is a good place to start. So we can rewrite this equation with a 2 coefficient in front of the diphosphorus pentoxide, giving us 10 oxygen atoms. That's an even number, whereas before we had it the odd numbered 5. So when we do that change, notice that we are also affecting the phosphorus atom. So we need to go back and rebalance phosphorus because it has been affected. So we need to look back at the starting phosphorus and put a 4 coefficient in front of it to balance it out on the left and on the right. We also need to rebalance the oxygen to make it equal 10 on the left. So if we put a 4 in front of the P and a 5 in front of the oxygen, we get to a completely balanced equation. So if you got that, great job. Now, the next example, actually, I want to give you one that's a little more fun than the one that I originally had written here. So what I want you to do is try this next one instead. So I'm going to write down the formula. What I'd like you to do is do the same, and then pause the video and see if you can apply any of the tips and tricks I've shown you so far to balance this equation. Okay, so if you're ready to get started, notice in this equation that we have a metal present, namely potassium, and the potassium is already at the beginning unbalanced. So that would be a great place to start, by balancing metals first. So how do we balance the metals? Well, if we have 3 on the right, we need to have 3 on the left as well. So we can balance this potassium by putting a 3 coefficient right in front of the potassium hydroxide. Okay, so let's write out the rest of the equation and then figure out where to go next. So potassium is now balanced. Notice that when I balance potassium, though, that it has an effect on the number of hydroxide that is present. So what that means is I need to rebalance that part of the equation next. And remember this tip I showed you, that the number of hydroxides should be equal to the number of waters on opposite sides of the reaction. So if I have 3 hydroxides on the left, I should have 3 waters on the right. So that's actually what I'm going to fix next. I'm going to change the coefficient in front of water and make it a 3, so that water balances with hydroxide. Okay, so now that we have that balanced, let's do a check and see if there's anything else that we can balance. So the first thing I'm going to do is I'm going to add up all the hydrogen atoms, and we see there are 6 on the left and 6 on the right. I'm going to balance make sure the phosphate is balanced, so we see there's 1 on the left and there's 1 on the right. And finally, I'm going to check to make sure potassium is balanced. It should be, since we did that first. So we have 3 on the left and 3 on the right. And we see basically we're good. So the oxygen atoms, if we add those up, there's 3 on the left, 3 on the right. So yeah, this is good. So that's basic introduction to balancing equations. What we're going to do in the next lesson is I'm going to teach you about some overview of the types of chemical reactions that we will run into in this course. So I'll show you the 5 different types of reactions. We'll break that up into 2 different lessons. So we'll learn a few at a time. And then in each case, I'll show you some example reactions of those. And we'll have a chance to practice this balancing on each of those types. So you will get a lot of opportunity to practice balancing, and actually through the rest of the course you're going to get a lot of chances to, whether you want them or not, I guess, to write out equations from sentences and from other types of things, and then you're going to have to balance them each time. And I'm going to show you as we go sort of what I like to think of as sort of a 3-step process when we're writing equations. And we're going to learn about those 3 steps and how to apply them consistently and generally arrive at good quality, easy to write chemical reactions. So with that, I'm going to end the lesson. Thanks for watching. Let me know if you have any questions, and I will see you soon. Bye.